Welcome to Mathematical Analysis. Today, we are diving into the fascinating world of derived sets. Imagine trying to find the most crowded, densely packed locations in an infinite mathematical universe. That is exactly what we will be doing. We will learn how to identify these points of infinite crowding, understand their strict mathematical definitions, and see how they form the hidden skeleton of the spaces we study. Let us get started. To begin, let us build our intuition. Imagine a massive outdoor music festival spread across a huge park. Some areas are completely empty, while others have massive crowds packed tightly together. If you stand in the middle of a dense crowd, no matter how small of a circle you draw around yourself, there will always be other people inside that circle with you. In mathematics, a point that always has other points of a set crowded arbitrarily close to it is called a limit point. The derived set is simply a special VIP master list of every single location that has this kind of infinite crowding. Now that we understand the intuition, let us define this formally in the language of real analysis. Suppose we have a set of real numbers which we will call S. A point is considered a limit point of S if every possible neighborhood around it contains at least one point of S that is different from the point itself. Think of a neighborhood as a small bubble surrounding our point, no matter how tiny that bubble might be. The derived set of S is defined as the set containing all these limit points, and we denote it using a prime symbol, S prime. Let us translate our bubble concept into strict mathematical notation. This formula might look intimidating, but it perfectly describes our crowded points. Conceptually, it tests every real number x to see if it qualifies as a limit point. The symbol epsilon represents a strictly positive distance, which creates our neighborhood bubble around the point x. As epsilon gets smaller and smaller, the bubble shrinks. The \x means we remove the exact center point from our bubble, because a limit point must have other points of the set nearby, not just itself. Finally, the intersection with S not being empty means our punctured bubble always shares at least one point with the original set. This formula we just saw leads us to an important question. What happens if our set only has a few specific numbers, like a set containing just the numbers 1, 2, and 3? It is a fundamental rule in mathematical analysis that the derived set of any finite set is always completely empty. To understand why, remember that a limit point requires an infinite number of points to be crowded arbitrarily close to it. If a set only has a finite number of elements, you can always draw a tiny bubble around any point that is so small it catches absolutely no other points. Therefore, there are zero limit points and the derived set is the empty set. Now that we know what happens with finite sets, let us look at how derived sets help us classify other types of sets. The concept of a derived set gives us an incredibly powerful way to understand closed sets. A set is closed exactly when it contains its own derived set. Think of a closed set as a secure vault that has already captured every single one of its infinitely crowded points inside its walls. Furthermore, there is a fascinating special case known as a perfect set. A perfect set is exactly equal to its own derived set. This means the set contains all of its limit points and absolutely every single point inside the set is also a limit point. Before we move on, let us see this with a concrete example. Let us find the derived set of the set S containing all fractions of the form 1 over n, where n is a natural counting number. Conceptually, this formula simply lists the elements of our set by plugging in the counting numbers 1, 2, 3, and so on. As the denominator n gets larger and larger, the resulting fractions get smaller and smaller. If you increase n, the physical distance between consecutive points shrinks rapidly as we move down the number line. We must observe where this endless march of shrinking fractions is ultimately heading to find our limit points. Let us solve this step by step. We are given our set of fractions and we are asked to find its derived set. We need to visualize these points on a number line to see where they crowd together. To do this, we take the mathematical limit as n approaches infinity. This shows us the ultimate behavior of the sequence. The calculation reveals that the values are marching steadily toward the number 0 without ever actually reaching it. This means that no matter how tiny of a neighborhood bubble you draw around 0, eventually the fractions will become small enough to fall inside that bubble. Continuing with our sequence, we see that because infinitely many points fall inside any bubble around 0, 0 is definitively a limit point. Furthermore, because 0 is the only location on the entire number line where these points bunch up infinitely closely, 0 is the only limit point. Notice a fascinating detail here. The number 0 is actually not in the original set S because 1 divided by n never exactly equals 0. However, 0 is still the limit point. Therefore, our derived set contains exactly one element. The final answer is simply the set containing the number 0. Now that we have calculated the derived set, let us look at exactly what this means visually. Here you see the real number line. The blue dots represent our sequence: 1, 1/2, 1/3, and so on. As you follow the blue dots to the left, notice how the physical distance between them shrinks. They pack so tightly together near 0 that they become indistinguishable. The red dot at 0 is our limit point. The shaded region represents our epsilon neighborhood bubble. No matter how much you shrink that bubble, an infinite number of blue dots will always be trapped inside it. This visual crowding is exactly what the derived set captures mathematically. Let us explore another scenario by looking at a continuous space. For our second example, let us find the derived set of the open interval from 0 to 1. Conceptually, this formula uses set builder notation to define a continuous segment of the number line. It contains all real numbers strictly between 0 and 1, but it explicitly excludes the boundary numbers 0 and 1 themselves. If you increase x, you move from left to right across the interval. We must check every point inside the interval and carefully check the boundary points to see if they have points of S crowded around them. Let us break down the solution for this open interval. We are given the continuous open interval from 0 to 1, and we need to find its derived set. First, we test the points strictly inside the interval. If you pick any point inside, such as the number 1/2, you can always find other points in the interval arbitrarily close to it. Because the real numbers are continuous, you can zoom in as much as you want, and you will still see an infinite number of neighboring points. Therefore, every single point inside the open interval automatically qualifies as a limit point. Continuing our analysis, we must now test the boundary points, which are the numbers 0 and 1. Even though 0 and 1 are not inside the original open set, any bubble drawn around 0 will capture positive numbers like 1000 that are inside the set. Similarly, any bubble around 1 will capture numbers like 9900s. Thus, both 0 and 1 satisfy the definition of a limit point. Combining all the limit points from inside the interval with the limit points on the boundaries, we get the closed interval from 0 to 1. This perfectly illustrates how a derived set naturally closes an open interval. Now that we have solved these examples, you might wonder why derived sets matter in the real world. In physics and engineering, derived sets help us understand the stability of systems and the boundaries of physical phenomena. For example, when studying the chaotic motion of a pendulum or the complex orbits of planets, scientists look for attractors. These attractors are essentially limit points where the system tends to settle over time. The derived set gives us a complete mathematical map of all these potential settling points, providing the foundation for understanding where things accumulate or stabilize in any continuous space. Let us summarize the key takeaways from our journey today. First, remember that a limit point is a location where the elements of a set crowd together infinitely closely. Second, the derived set is simply the master collection of all these limit points. We also learned that finite sets lack this infinite crowding, so their derived sets are always empty. Finally, we saw how derived sets naturally define closed sets and reveal the hidden structure and boundaries of mathematical spaces. You have now mastered the foundational concepts of derived sets, unlocking a deeper understanding of real analysis. Excellent work!